You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your ITIL Foundation certification journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. The guiding principle of optimize and automate recognizes that efficiency comes not from working harder, but from working smarter. Optimization and automation are complementary strategies, each reinforcing the other. Optimization ensures that workflows are streamlined, waste is reduced, and processes are effective in their current form. Automation then applies technology to execute these improved processes at scale, delivering speed, consistency, and reliability. Together, they create systems that are both lean and resilient. The order matters. Optimization always comes first. Automating broken or inefficient processes simply multiplies waste. By combining careful analysis with technological execution, organizations achieve efficiencies that are not only faster, but also smarter. This principle reminds us that effective efficiency is deliberate, built on a foundation of thoughtful design before being accelerated by tools. Optimization can be defined as the systematic improvement of flow and performance. It involves analyzing how work moves through a process, identifying inefficiencies, and making changes that improve speed, quality, or cost-effectiveness. Optimization is not random tinkering. It is a structured discipline grounded in measurement and analysis. For example, optimizing an incident management process may involve simplifying categorization, reducing unnecessary approvals, and aligning staffing with demand patterns. The goal is to make the process smoother, faster, and more predictable. By focusing on optimization first, organizations ensure that processes are stable and effective before layering on automation. Optimization lays the groundwork, creating processes that are worth automating in the first place. A critical principle is that optimization must precede automation to avoid encoding inefficiency. Automating a flawed process does not solve its problems, it magnifies them. For instance, if a service request process requires redundant approvals, automating it will only deliver faster redundancy. The result may be worse, as inefficiencies become harder to change once they are codified in software. By optimizing first, organizations identify and eliminate waste, clarify responsibilities, and simplify workflows. Only then is automation applied, amplifying efficiency rather than entrenching waste. This sequence ensures that automation builds on a solid foundation, avoiding the trap of fast but wrong. The mantra is simple but powerful. Optimize first, then automate. Identifying constraints and bottlenecks is a natural starting point for optimization. A bottleneck is a step in the process where work piles up, slowing down the entire flow. Constraints are factors that limit performance, such as limited staff, outdated technology, or cumbersome policies. By targeting these areas, organizations can often achieve outsized improvements. For example, if ticket resolution is delayed because only one specialist can approve escalations, broadening approval rights may eliminate the bottleneck. Identifying and addressing constraints turns isolated frustrations into system-wide improvements. Optimization requires this kind of focused analysis, where the goal is not to change everything, but to identify the few key obstacles that restrict overall performance. Waste categories provide another lens for optimization. In service work, waste often appears as rework, waiting time, overprocessing, or unnecessary approvals. Rework occurs when tasks must be repeated due to errors or unclear requirements. Waiting time arises when work sits idle between steps. Overprocessing occurs when more effort is applied than stakeholders actually require. By identifying these forms of waste, organizations can streamline processes and reclaim lost capacity. For example, eliminating duplicate data entry can reduce both errors and delay. Lean-inspired thinking encourages organizations to treat waste as a solvable problem rather than an inevitable cost of doing business. By rooting out waste, optimization clears the path for value to flow more directly. A value stream perspective sharpens this focus by looking at the end-to-end flow of work, from demand to value realization. Mapping value streams helps organizations see where work adds value and where it does not. For instance, in a service request process, capturing user needs and delivering the solution add value, while excessive approval loops may not. By analyzing the stream holistically, teams can see the cumulative effect of small inefficiencies and identify opportunities for improvement. Value streams also provide a way to prioritize optimization by showing which steps are most critical to delivering outcomes stakeholders care about. This perspective ensures that changes improve the whole flow, not just isolated steps. Optimization depends on baseline measurement. A baseline is a documented reference point for current performance against which improvements can be compared. Without it, claims of progress remain subjective. For example, if average ticket resolution time is currently 24 hours, that baseline provides a benchmark for evaluating whether optimization reduces it meaningfully. Baselines also help organizations communicate improvement clearly, showing stakeholders tangible evidence of change. Establishing baselines is not about creating perfect measurements, but about creating consistent ones. They provide the anchor that makes improvement visible, credible, and sustainable. Metric selection is a related discipline that ensures measurement aligns with outcomes that matter. The danger is selecting metrics that are easy to collect but irrelevant to value. For instance, counting the number of incidents logged may say little about actual service performance. More relevant metrics might include mean time to resolution, user satisfaction, or reduction in repeat incidents. Metrics must also provide quality signals, clear, timely, and reliable indicators of performance. Poor metrics distort decision-making, while well-chosen ones illuminate reality. By focusing on outcome-relevant metrics, optimization efforts remain anchored in what stakeholders truly value rather than in vanity measures. Root cause analysis ensures that optimization addresses systemic issues rather than superficial symptoms. Problems often appear in one area but originate elsewhere. For example, repeated login failures might appear as a user error issue, but root cause analysis might reveal inconsistent synchronization between identity systems. Addressing the root cause eliminates the problem permanently, rather than patching symptoms repeatedly. Root cause analysis requires disciplined inquiry, asking why multiple times until the true source is uncovered. By targeting causes rather than symptoms, organizations maximize the impact of their optimization efforts and prevent recurrence of issues. This discipline transforms firefighting into meaningful improvement. Standardization supports optimization by reducing variation and error probability. Standard work means that tasks are performed consistently, making outcomes more predictable and less prone to mistakes. For example, a standardized onboarding process ensures that all new employees receive the same essential tools and permissions, reducing the risk of missed steps. Standardization also simplifies training, since staff can rely on clear, repeatable procedures. It forms a stable foundation on which further improvements and automation can be built. Without standardization, optimization efforts may falter, as unpredictable variation undermines consistency. By embedding standards, organizations ensure that optimization produces lasting gains rather than short-lived fixes. Simplification of steps is another way to optimize by reducing cognitive load and defect rates. The more steps a process contains, the more opportunities there are for mistakes and delays. Simplifying steps reduces complexity, accelerates execution, and increases reliability. For instance, consolidating 3 separate forms into one streamlined request reduces user confusion and staff rework. Simplification does not mean removing safeguards, but ensuring that each step adds value. By questioning whether each action is truly necessary, organizations can uncover hidden complexities that have grown over time. Simplifying processes not only improves performance, but also makes them more suitable for automation later. Risk assessment is essential to optimization because improvements must not degrade assurance. Every change carries potential risks, and optimization must consider whether those risks are acceptable. For example, Removing an approval step may accelerate a workflow but could also reduce oversight. Risk assessment ensures that changes strike the right balance between speed and safety. By analyzing likelihood and impact, organizations can adjust optimization efforts to preserve essential safeguards while removing unnecessary friction. This discipline ensures that optimization produces sustainable gains that support both performance and trust. Documentation also supports optimization, but the principle of just enough applies here as well. Excessive documentation creates overhead, while insufficient documentation undermines repeatability. The right balance is documentation that is accurate, accessible, and sufficient for the task at hand. For instance, a one-page checklist for incident escalation may be more useful than a 50-page manual. Just enough documentation keeps processes consistent without drowning teams in paperwork. It also lays a foundation for automation, providing clear instructions that can later be encoded into systems. By documenting wisely, organizations strengthen both human and automated performance. Governance alignment ensures that optimization objectives match the organization's strategic direction. Improvements must not only make processes faster or cheaper, they must also support broader goals. For example, simplifying a reporting process may be valuable, but if it undermines regulatory compliance, it creates long-term harm. Aligning optimization with governance ensures that efficiency never comes at the cost of accountability. It connects local improvements to enterprise priorities, ensuring coherence and sustainability. Without governance alignment, optimization risks creating isolated gains that conflict with larger objectives. Holistic alignment ensures that optimization is both responsible and strategic. Finally, stakeholder involvement validates that optimization increases perceived value. Improvements that look good internally may not matter to customers or users. For example, reducing internal handoffs may delight staff but have little impact if users still face long wait times. By engaging stakeholders, organizations test whether optimization aligns with what matters most. This feedback ensures that improvements are not only efficient but also meaningful. Stakeholder validation reinforces trust and increases adoption of changes. It also highlights areas where optimization can be refined further. Ultimately, optimization must always serve value, and only stakeholders can confirm whether value has truly increased. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Automation can be defined as the use of technology to perform repeatable tasks with minimal human intervention. Where optimization refines and simplifies, automation executes and scales. Its power lies in delivering speed, consistency, and reliability, while freeing people to focus on higher-value activities. For example, automatically routing service desk tickets based on category eliminates repetitive sorting work and reduces delays. Automation is not about replacing people entirely. It is about rebalancing effort so that human judgment is applied where it matters most. By defining automation in this way, organizations see it as a supportive partner rather than a threat, ensuring that both technology and people contribute to service excellence. Not all tasks are suitable for automation, which is why candidate selection is crucial. Tasks that are high-frequency, effort-intensive, or prone to human error often make the best candidates. For example, nightly system backups, password resets, or routine monitoring checks are ideal for automation. By contrast, tasks requiring nuanced judgment or complex exception handling may not be good fits. Assessing candidates involves weighing frequency, volume, effort, and risk. Automating rarely performed tasks may not justify the investment, while automating sensitive activities without safeguards may create new risks. Careful selection ensures that automation produces meaningful gains in efficiency without undermining assurance or value. Workflow automation goes beyond individual tasks, orchestrating activities across tools and teams. For example, when a user submits a service request, workflow automation can log the ticket, check eligibility, notify approvers, and trigger fulfillment all without manual intervention. This orchestration reduces delays and ensures that work flows smoothly across boundaries. It transforms service delivery into a predictable, transparent process where each step is automatically tracked. Workflow automation also supports consistency, ensuring that rules are applied the same way every time. By coordinating multiple tools into a unified flow, organizations prevent gaps and handoff failures that plague manual systems. Policy as code is an advanced form of automation where organizational rules are translated into machine-executable logic. Instead of relying on manual enforcement, policies are embedded directly into systems. For example, access control policies can be encoded so that users requesting elevated privileges must meet predefined conditions automatically validated by the system. Policy as code reduces reliance on human oversight, speeds decision-making, and ensures consistent compliance. It also supports auditability, as every decision is traceable to coded rules. This practice exemplifies the principle of automation by showing how governance itself can be enforced automatically, balancing efficiency with assurance. Robotic process automation, or RPA, represents another branch of automation focused on interface-level tasks. RPA tools mimic human interactions with applications, performing actions such as copying data between systems or filling out forms. For example, an RPA bot might extract invoice data from emails and input it into a financial system. RPA is valuable for bridging gaps where full integration is not feasible. While not as elegant as system-level automation, it delivers quick wins by reducing manual effort and error in repetitive, rule-based tasks. RPA demonstrates that automation can take many forms, ranging from lightweight bots to deeply integrated workflows. Event-driven triggers integrate monitoring systems with automated actions, creating responsive environments. For instance, if a server exceeds CPU thresholds, an automated action may allocate additional resources or restart services. Event-driven automation ensures that systems adapt dynamically to conditions without waiting for human intervention. This reduces downtime, accelerates recovery, and preserves performance. It also illustrates the synergy of optimization and automation. Monitoring provides visibility into performance, while event-driven triggers provide the agility to respond instantly. Together, they create ecosystems where issues are contained before they escalate, reducing impact on stakeholders and reinforcing trust in service reliability. Human-in-the-loop controls are an important safeguard in automation, ensuring that certain steps remain reversible and auditable. For example, an automated patch deployment system may prepare updates automatically but pause for human approval before applying them to production. This approach balances efficiency with oversight, allowing humans to intervene when risks are high. Human-in-the-loop models prevent automation from becoming reckless, ensuring that judgment and context are applied where needed. They also reassure stakeholders that automation is accountable, not opaque. By designing automation with checkpoints for human review, organizations build trust and preserve adaptability while still benefiting from technological speed and consistency. Change enablement must extend to automation itself. New automations, like any change, can introduce risks if deployed without safeguards. For example, automating account termination may inadvertently remove active users if rules are misconfigured. Change enablement for automation includes testing, staged rollouts, and approval processes tailored to risk. It ensures that automation is deployed responsibly, with governance oversight proportional to its impact. By treating automation as a change, organizations integrate it into existing assurance frameworks, reducing the chance of disruption. This discipline prevents automation from being introduced carelessly and reinforces the principle that efficiency must never come at the expense of stability. Version control and continuous integration practices extend naturally to automation artifacts. Scripts, workflows, and bots are themselves forms of code and require the same rigor as software development. Version control ensures traceability, allowing teams to roll back to previous versions if problems occur. Continuous integration pipelines allow automated testing of automation logic before deployment. For example, an automated workflow for provisioning servers can be validated in a test environment before release. These practices embed reliability into the automation lifecycle, preventing errors from spreading into production. They illustrate that automation is not a shortcut but a discipline, requiring the same governance as other critical assets. Observability is essential for monitoring automation in action. Logs, metrics, and traces provide visibility into what automations are doing, how often they succeed, and where they fail. Without observability, automation becomes a black box, eroding trust and complicating troubleshooting. For example, monitoring might reveal that an automated report failed to run due to a configuration change, enabling quick correction. Observability transforms automation from hidden machinery into a transparent partner, making its actions visible and accountable. This visibility ensures that automation remains aligned with stakeholder expectations and continues to deliver value over time. Reliability patterns strengthen automation by handling the inevitable uncertainties of real systems. Techniques like rate limits prevent overload, retries address transient failures, and ID impotency ensures that repeated actions do not cause harm. For example, an automated payment system must be idempotent so that retrying a failed transaction does not charge a customer twice. These reliability patterns transform automation from brittle scripts into robust systems capable of handling real-world variation. By designing with reliability in mind, organizations prevent small hiccups from cascading into large failures, ensuring that automation sustains trust rather than undermining it. Failure handling choices also illustrate the nuance of automation. Some systems adopt a fail-open approach, where automation halts and hands control back to humans in case of error. Others use fail-closed, stopping processes entirely to prevent unintended consequences. For instance, an automated firewall update might fail closed, blocking changes until reviewed, while an automated reporting system may fail open, allowing manual workarounds. The choice depends on risk tolerance and context. Designing failure handling thoughtfully ensures that automation remains safe and predictable. It reinforces the principle that automation must always serve value, never jeopardize it. Ownership models provide the governance necessary for sustainable automation. Every automation requires clear responsibility for maintenance, incident response, and ongoing improvement. Without ownership, automations quickly degrade, causing confusion and risk. Ownership may be assigned to a team, such as infrastructure or operations, with defined roles for monitoring and updates. For example, an RPA bot extracting financial data should have an accountable owner responsible for ensuring accuracy and adapting to system changes. Ownership ensures accountability, preventing automation from becoming orphaned and neglected. It also ensures that automation evolves alongside organizational needs rather than becoming static and fragile. Cost-benefit evaluation must also accompany automation decisions. Building and maintaining automation consumes resources, and not all investments yield worthwhile returns. For example, automating a rarely performed task may cost more to design and maintain than it saves in effort. Evaluating costs, operational savings, and risk reductions ensures that automation investments are justified. This evaluation also considers intangible benefits, such as improved accuracy or faster stakeholder response, alongside tangible savings. Cost-benefit analysis ensures that automation is not pursued for its own sake, but as a deliberate choice aligned with strategy. It grounds automation in practicality, reinforcing its role as a value enabler. From an exam perspective, the essential message is clear: optimize first, then automate. Questions may present scenarios where an inefficient process is being considered for automation, and the correct answer will emphasize optimizing the workflow before applying technology. Learners must also recognize automation practices such as workflow orchestration, event-driven triggers, and human-in-the-loop safeguards. The exam perspective reinforces that automation is not a panacea. It is a multiplier of whatever process it is applied to. If the process is good, automation amplifies value. If the process is flawed, automation amplifies waste. Mastering this principle ensures that learners can apply it responsibly in both theoretical and practical contexts. In conclusion, optimization and automation are twin pillars of efficiency. Optimization streamlines processes, clarifies steps, and removes waste. Automation then accelerates these optimized processes, delivering speed, consistency, and reliability. When applied in sequence, they create services that are lean, resilient, and responsive. When misapplied automation before optimization, they entrench inefficiency and risk. By embedding practices such as workflow automation, policy as code, observability, and ownership models, organizations ensure that automation serves value rather than undermining it. For learners, the takeaway is clear: measured optimization enables safe and valuable automation. Efficiency is achieved not by shortcuts but by disciplined, thoughtful design followed by technological execution. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.